Good morning, my name is Vincent Gruwez from the Department of Civil Engineering at Ghent University. Now looking at this picture, what do you see? Maybe it reminds you of a beach trip, maybe you see some interesting features related to your field of interest. But me as a coastal engineer, what do I see? I see a coastal defense system. This is what protects us from flooding during storm conditions. The most obvious part being the dike itself with the dike slope, promenade, maybe a storm wall on top, and which protects the apartment buildings and hinterland from flooding. But also the beach in front of the dike plays a very important role. This is illustrated in this picture where you see a beach scarp or erosion cliff that people tend to complain about in the news after every moderate storm. It actually shows that the beach is performing its job as a coastal defense system by providing an erosion buffer and keeping the sea away from the dike. That's for moderate storms. What happens in more extreme cases, like a superstorm? The water is pushed even higher up to the dike, and still in this case the beach plays a very important role, in this case as a very shallow foreshore. This means that the water depth from offshore is decreased significantly up to the dike, forcing the waves to break, losing a lot of energy before interacting with the dike, like overtopping and wave impacts on structures on top of the dike. Now, all these processes that I've described are what makes this coastal defense structure so complex and challenging to design for. And that's where my research fits into, because I'm working towards an improved numerical modeling methodology for this specific case. Now, how am I achieving this? Well, of course, by numerical modeling, but a numerical model will always give me a result. The important question to ask is, can I rely on this result? So we need to compare it to both experimental modeling and field measurements. But more on that later. Let's first look at the model, numerical model results, and you again recognize the beach indicated in yellow, and in black the dike here. And indeed, waves are breaking over the beach before interacting with the dike. Now, if we zoom in a little bit more to the dike itself, here I've compared the numerical model results with experiments that for which we obtained surface elevation measurements at these locations, and pressure impacts and wave forces on the vertical wall. And as I start this video, you can follow in the top graphs the dashed line, which represents the numerical model results, and you can compare it to the black line, which is the experimental modeling results. And you will immediately notice there is a slight time shift, but what is important here is that the magnitude and evolution in time corresponds very well with the experimental modeling, confirming that the numerical model gives a reliable result. Now, future work will include comparing the numerical model to more complex situations that we have tested in our wave flume, where we generate waves at one end, and they propagate towards the dike. Well, they break again, of course, and then they start interacting with the dike. But we have obtained a high spatial resolution of surface elevations, but also wave overtopping here at the dike crest, and wave force measurements at the vertical wall. One disadvantage of experimental modeling is that we need to scale everything down, so we introduce some scale effects. We don't want that. Well, it's a disadvantage, and that's why it's crucial that we also need to do field measurements. Now, the chance of a superstorm occurring in any given year is very low, so we cannot do these measurements on the existing dike. So what we will do is we will build an artificial dike on the beach to effectively bring the dike closer to the sea, enabling us to do these kind of measurements in yearly storms. Now, for the artificial dike, we've also done some experimental modeling, as you can see here. It will serve as input for our detailed design later this year so that we can start measuring in next winter. Now to conclude, I'm working towards an improved numerical modeling methodology, thoroughly validated by experimental modeling and field measurements, so that you can have a much more optimized design of this type of coastal defense structures with very shallow foreshores. Okay, thank you for your attention.